As we start talking about calculus, there's something that we have to talk about first, which is the notion of limits. You see, limits are very important because they help us answer a very particular type of question, namely, what should be happening? And in particular, what should be happening when we get to 0 over 0, which is a very common occurrence that we have. So we want to take a little bit of time to talk about what's happening with the limits of multivariable functions, what we can do, and a little bit about what we can't do. And let's just say things get a lot more interesting. Let's begin. So let's start by asking the question, why is division by 0 bad? And it turns out that you can say, well, look, if I have A divided by B equals C, that's the same as saying, look, A is B times C. So what happens when our B is 0, right? Our denominator is 0. Well, that would say, look, A has to equal 0 times C equals 0. Now there's two possibilities. If A is not 0, well, we say, wait, A has to be 0. So A can't be 0. That's impossible. Okay. But the more interesting thing is if A equals 0, in other words, 0 over 0, it's ambiguous in the following sense. In the sense, what should have you picked for C? You could have picked anything for C, and it would still be a true relationship. So it's not clear what it should be. So what do we do? Our answer is to say, well, look, if we come into a situation where we have a 0 over 0, instead of asking the question, what is it? We change our question. And we say, what should it be? In other words, as we sort of get closer and closer to what's causing that 0 over 0, what can we say about the expression? What's happening nearby? And based on what's happening nearby, that will be what should happen. I'm going to say that's the limit. So the important takeaway is limits are what should happen. So we write our limit as our point xy gets closer to our point AB of f of xy equals L. Well, what is that saying? Well, our inputs, we're thinking of it as a pair of coordinates. So as a point, xy, are getting close to a very specific, specified input, AB. So we're saying, well, what's happening as we're getting close? And the answer is, well, it appears that for that particular function, all the values near the point AB are close to L. Now that's the intuitive thing. Of course, we can get technical. So what's the technical thing? We say, for every epsilon, there's a delta. Now, oftentimes you're like, whoa, wait, where did epsilon and delta come from? Because when we talked about our sort of intuitive definition, there was no epsilon and delta. So the idea is you'll see that there's this key word, close and close. We're actually close in two different ways. So what epsilon and delta are measuring is they're a measurement of closeness. How close are we? The epsilon says, I want to measure closeness in output. So the difference between f, the function, and L, what I think the limit should be. I want to guarantee that's small. And we're saying, look, we can guarantee the output is small as long as we can guarantee the inputs are sufficiently small. So in other words, no matter how small we want to be over on this part, we say, look, if you make it really, really small, not 0, but small enough, then we're okay. So that's where our epsilon is a measurement of distance in output. Delta is measurement of distance in input. So that's the idea. Now, if you go back and look at limits in Calc 1, you'll say, it's basically the same definition because it's the same ideas. It's all about measuring closeness. What's happening? What should it be? So we still have our wonderful basic properties. Namely things like if we know a limit of f is L, the limit of g is m, the limit of f and g together, well, we add L plus m, right? If f is getting close to L, g is getting close to m, then f plus g is getting close to L plus m. So in other words, they behave intuitively. So they work well with addition. They also work well with multiplication. It's L times m. It even works well with division as long as we're not dividing by 0. And then one other thing is, of course, continuity. So suppose we have a continuous function, and we'll do a function of a single variable, and it's continuous at some value. Well, we say, look, h of f of xy, we can pass the limit through. See, that's the key idea, is we're passing the limit through into the inside of the continuous function, which is why we like working with continuous functions. In other words, continuous functions are functions with no surprises. And that's our definition. So in particular, here we go. See, look, a function is continuous if what we think should happen, which is talking about the limit, is what does happen. In other words, the value of the function. Now, most of the functions we deal with are continuous. They're actually even better than continuous. They're smooth. We'll talk about what that means in future sessions. But things like polynomials, your trig functions, your exponential functions, even your square roots, your logs. And there are some functions with asymptotes. As long as you are out from the asymptotes, you're fine. Now, because of the way that we have these combinations of functions, in other words, remember that we can add limits, we can multiply limits, we can put a limit inside of a continuous function. What it really says is, hey, once you have a couple of basic building blocks, it's very easy to build up continuous functions, to the point where pretty much anything we write down using our tools like addition and multiplication and powers and exponents and so forth, as long as it's defined, that's continuous. So it makes it very nice. In particular, it works very well with limits. That'll be one of our strategies. In fact, we're going to talk about several different strategies. Okay, so what's our goal? Our goal is we have a limit. We want to figure out what is the limit. Well, let's talk about our strategies. Now, the first strategy is fantastic. It says, hey, suppose you're working with a continuous function. Then the continuous functions are functions with no surprises. So what do? It says, look, if your function is continuous, just plug it in and you're done. So in other words, what this is saying is, look, the limit as xy approaches ab of f of xy is equal to f of ab. Of course, this assumes f continuous. So you take a look at the function, you say, okay, are the individual pieces continuous? Are they put together in ways which are compatible with continuity? And the answer is yes, you just plug it in. If you get a reasonable answer out, then you're done. That should always be the first thing you try. You should always say, let me plug it in and see what's happening. Pretty much as long as you don't get a 0 over 0, you can say what the answer is, and you're done. Okay, but of course now the interesting 0 over 0, which we know means more work. Because when we see 0 over 0, we know it's possible it could be many things. That's the point of 0 over 0. There's ambiguity. So strategy number 2, what is that? Well, think back to limits in one variable. One of the things that we would do is we would say, let's compare the two different directions. So what could happen is we could come in from below or from the left, or we could come in from above, from the right. So we could think about doing it in two ways. This was oftentimes used when we had piecewise, but nevertheless, we could think about coming from our two sides. Now, the nice thing is if you think about one dimensions, because we have one variable, there's really only two different ways we can approach. Either coming from below or coming from above. That's it. Which says, hey, let's just look at all the ways we could approach and compare. Now, if we ever had this going on, where in other words, as we came from the two sides, we got different values, then there was no limit. The same principle applies. It says, hey, think about your point. See, now we have two inputs, x and y. So we can think about how do we get close to that point. And we can say, look, if we ever have something like this, where depending upon how we approach, because we can approach from different directions now, but if we approach and they go to different values, then the limit doesn't exist. So, how many ways are there to approach our point? You're probably thinking, okay, well look, we can still approach from the sides, right? Sure, no problem. You can approach from the sides. Well, that's if we hold one variable constant and let just the other variable vary. Is that it? Well, no, you could approach from up and down, right? Sure, all right. Is that it? No! You could approach from any straight line you want. You're like, wow, that's crazy. But surely that's enough. Well, is it? And the answer is no, because we can be creative. So creative. We could do crazy things like we could come along some sort of curve. We could come along a squiggle. We could even, if we wanted to, we probably wouldn't, but we could even spiral in. There's lots and lots of different ways. And indeed, there are essentially an unbounded number of ways to approach. So we run into this sort of interesting problem. See, in single variables, since we only had two ways, we only had to check the two different possibilities. But because we have all this freedom of movement in the plane, we cannot prove a limit exists by checking every possible approach, because you can't check every possible approach. There's just too many of them. But what we can do is prove it doesn't exist if we can find two different approaches that don't match. So, this is important, this warning. We only pull this out if we think that the limit doesn't exist, because that's the only time we can actually use it. If the limit did exist, forget it. We couldn't do anything. So, all right. So I will tell you, by the way, this is kind of the fun one, because it says, what do? Well, you explore. You say, let me think of different ways I can approach the particular input, A, B, and maybe I can find a way that's even better so that it all works out. All right, good. Now, strategy number 3 is squeezing. So in other words, you want to bound something above and below by two functions which are easier to work with. So what's going on? Well, the idea is actually not so bad. You say, look, I have a function I'm interested in, say f of xy. If you can bound it above, let's say by h of xy, and below by g of xy, and these are both nice. So here that we have as our point xy heads towards AB, well, maybe f of xy goes to L and g of xy goes to L. In other words, both f and g are close to L. Well, where is f? It's got to be somewhere in the middle. So if g goes to L and h goes to L, then f, the one in the middle, also will go to L. So that's the idea of squeezing. Now, how do we actually use it? Sometimes it's subtle, sometimes it's not. But really what you're looking for is if you can say, there's a part which is messy, but I can bound it. And the other part I can control and show it gets small, then you're good. So what you're really looking for when you're thinking about using a squeeze principle, the most common way you'll see it is you'll get something small times something which is bounded. And when you combine these together, you see, aha, the net result is small. So when I talk about small, what I mean is something going to 0. Now, what do I mean by something which is bounded? Well, something which can't get arbitrarily large. It has to stay within some fixed range. The classic example of things which are bounded are things such as sine of something or cosine of something. Because you might say, well, but they're just doing crazy. They're like, oscillating really, really rapidly close to where our point is. You're like, it's all over the place. We can't tell. But even though it oscillates a lot, it doesn't oscillate by much. It only goes between -1 and +1. So no matter how far we go up and down, it has bounded behavior. So if we can multiply by something which we know is getting small, then we've won the game. So that's a great way to do it, is by using squeeze. Okay, and this one takes a little bit of practice. It's not always easy to spot, but we'll have a chance to do some practice in our practice session. But general rule of thumb is, if you see something which is really bad, like a sine of something that oscillates a lot, you're like, but sine is bounded. That's one of your fun facts you should always keep in the back of your head. Sine and cosine are bounded. And so it's like, okay, given that I know it's bounded, can I make a conclusion about what the other part is doing? All right, now, you might say, can we do more? Yes, of course. Take more math classes. That's our fourth strategy. Now, of course, from my perspective, this is great. I'd love for people to take more math classes. Not because, I'm going to get paid more or anything, but just because I think math is wonderful. It's a great way to think about the world. What do you learn in more math classes? Well, you get better ways to write, better ways to bound, better ways to approximate, and there's a lot to do. And so this part of math, this calculus, is really something that falls in what's known as analysis. And to get good at analysis, one of the things you do is you start saying, all right, what can I understand as the important part? And what can I say, this is not important, throw it away? Well, it takes a lot of practice. And it's not so easy. Even for mathematicians who've been doing this for a long time, they're not going to just say, trivial. No, they're bluffing. They always have to think about it. Now, why are we doing limits? Where we want to get to is we want to get to derivatives. Derivatives are sort of our goal. How are functions behaving? How are they changing? So we say, okay, we know how to take derivatives. It's our limit as x goes to a, difference in our outputs over difference in our inputs. That's what it is. No problem. So I say, okay, well, if we're thinking about derivatives of multivariable functions, well, let's do the same sort of idea. We'll look at our difference in our outputs over difference in our inputs. Okay, well, our outputs, no problem. That makes sense. The difference in our inputs. So if I think about xy minus ab, well, what does that mean? Well, we can think of this as a vector. And we say, okay, all right, that kind of makes sense. But now we have our problem. We have a number divided by a vector. And we're like, whoa, we can't divide by vectors. So this is a #fail. No dividing by vectors. Okay, so we can't do our derivatives this way. You're like, okay, all right, good. Fine. No problem. Easy fix. The thing is that we're dividing by a vector. Let's divide by a number. So instead of taking the difference between 2 points, we'll just take the distance between 2 points. So the difference being the vector, the distance being how far apart are they? Well, now we at least have a number downstairs, and we say, okay, well, is this going to work? And, #subtle fail. Now, what's wrong? Why will this fail? Why does this not work? And the answer is it comes down to one important principle, and that is you're losing information. And the important thing that you're losing is you're losing orientation or direction. So when you think about what happens when we talk about single variable functions, the x minus a actually had a sign attached. So it wasn't just the absolute value of x minus a. It was like, well, x minus a was positive or negative, which was an orientation, a direction. Once you take the magnitude, you lose that orientation and you lose information. So it turns out something similar happens here. And so that will also fail as a derivative. It just won't work. And it really can't work. So now at this point, you're probably thinking, well, this is terrible. What are we going to do? And that is a wonderful discussion for our next session. But for now, let's go do some practice with limits. See you soon.